We're going to continue in Chapter 5, which is overall theme is the periodic table. And what we're going to look at now are the property of elements, valence electrons, and electron dot formulas. In this chapter, we want to make the connection between the location of an element on the periodic table and their chemical properties. We know that the elements follow regular repeating patterns. And so if we know how one element in a group reacts, then that pattern can help us predict what the other elements in that same group or column will do. So to rephrase that, you can see here on the periodic table, members of a group or family, and that's referring to the columns, have similar chemical properties. And so that is the concept we want to reinforce in this part of the video. So they give us an example from your textbook. Let me change here. And they take a look at the alkali metals, which are in the first column on the periodic table. It's group 1A. And when those metals react with oxygen, they make oxides, and they all have this same formula. So in that, the formula I circled, the M just means the metal. So it means whatever metal you are looking at from the alkali metal group. And so then they give us the examples where in each situation they've gone from the top of group 1A with lithium and the alkali metals, and they go down and they're writing the formulas for the oxides. So that's the pattern, that the alkali metals, when reacting with oxygen, for example, will have a 2-to-1 ratio. So let's see how we could use the idea of this periodic law and information given about a particular element to predict about other elements on the periodic table. So in this case, it says metallic sodium reacts with chlorine gas to give sodium chloride. Then the question says predict the product form when lithium and potassium react with chlorine gas. So looking on the periodic table, sodium is an alkali metal, and it is located right here. There's sodium. And so we know that sodium has a 1-to-1 ratio with chlorine when they react. And that was given to us in the problem. Now what they want us to do is predict what will happen when lithium, which is an element above, and potassium, the element below sodium, what will happen when those two elements react with chlorine gas. Predict the formulas. So pause the video now and you try to predict, and then I'm going to give us the answer. Okay. So if sodium chloride has a 1-to-1 ratio, then we would predict that lithium also would form a 1-to-1 ratio, and potassium would form a 1-to-1 ratio. On letter A, forming lithium chloride, and letter B, forming potassium chloride. So that's how we can use the periodic law to predict what elements what type of reactions or what type of compounds they will form. Now notice, to predict, we had to not only know where the element was, but we had to know what one of the elements in the group were doing. Now we can extend this to other elements on the periodic table. So this question says, which of the following metals has chemical properties most similar to, and then they say zinc. So zinc has the element symbol Zn, and so I would need to find zinc on the periodic table, keeping in mind that elements in the same group as zinc would be predicted to have similar chemical properties. So zinc has an atomic number of 30. It's right here. So let's look where the elements are that they have asked us to compare. So the first one they said is iron, which is right here, and then copper, which is right next to zinc, and then cadmium. So the question wants to know, of those three elements, which would most likely have similar chemical properties to zinc? So pause the video, get an answer, and then I'm going to answer it. All right, so periodic law says elements in the same group we would predict to have similar chemical properties. So since cadmium is below zinc, we would expect that cadmium and zinc would have similar chemical properties. So from this part of the chapter, I just want you to have a better understanding of what periodic law is. So what is periodic law and how we can use it to predict some chemical properties of elements in the same group. So now we're going to look at valence electrons. And before we get into valence electrons, I do know in Chapter 4 we did electron configurations. In that discussion, I also mentioned valence electrons, and we're going to just look a little closer. And for some of you, it might be a review. So I am not going to review here how to write electron configurations. If you would like to write electron configurations, then please go back to the video in Chapter 4 and review. Of course, you always can ask me questions or any of the tutors at the library. So it says, recall that here's the electron configuration for sodium. Okay, so sodium on the periodic table, I have a really tiny one here. It's probably hard to see, but there's sodium right there. And so the complete electron configuration for sodium is right here. Now, if I break this electron configuration down by its energy levels, I can see there's 3 energy levels. Here's the first energy level with the 1s2. The second energy level would be the 2s2, 2p4, and the highest energy level in sodium is just the 1 electron that's in the 3s1. So those are our energy levels. Now here, which I also went over in Chapter 4, is an abbreviated electron configuration. So in abbreviated electron configurations, they go to the noble gas that is before the element. So if we are right here with sodium, the noble gas before sodium is neon, and they put the symbol of that noble gas in a bracket. And what that tells us is up to neon, all the electrons are present. So thinking about electron configurations, they're saying the first energy level and the second energy level are all present. Then what you do is you write the electron configuration of whatever electrons are in the period or row that your element is in. So here it is 3s1. So in this particular situation, all we really see are what is in the outermost level of sodium. Okay, so that's just a reminder about electron configurations. So now another kind of reminder, I would like you to look at each one of these electron configurations and identify where the highest energy level is. So when we look at the electron configuration, determine which energy level represented is the highest energy level. You might want to pause the video now and try to do it on your own, and then turn the video back on and I'm going to answer it. All right, so hydrogen only has 1 electron, so its highest energy level is the only level it has, so it's just 1s1. Now in sulfur, I see that it has the first energy level, the second energy level, the third energy level. So the third level would be the highest. So right here, would be the highest energy level. And within that energy level, the highest one, there are 6 electrons. See, there's 2 plus 4. So this has 6 electrons in the highest energy level. Now, nickel has more energy levels. It's further down. So it has the first level, the second level. I see in the third level there's this, but also the 3D, and then I have the fourth level. Now, remembering on the periodic table, the 4 S's are lower in energy than the 3Ds, so the electrons will go into the 4 S's before they go into the 3Ds. So 3Ds do have slightly higher energy. But when you're asked about the highest energy level, you're looking for the number in front. So the 1s, the 2, the 3, and in this case, 4. So the highest energy level for nickel is 4s2. And that, if you see, has 2 oops, I didn't mean to make it that's 2 electrons. Then we go down to uranium, which it goes all the way down into the F sublevels. In general, I don't ask you to do anything in the S sublevels except perhaps on extra credit. But here it's given to us. We didn't have to write it. They've used abbreviated notation, which is very nice because otherwise uranium, which is element 90, would have to represent 90 electrons, but it's just representing the row that it's in. So we see there's electrons in 7, 6d, and 5f3. So while the 5f3 might be the last electrons in, if we were asked to find the highest energy level, then it would be this energy level 7, and uranium would also have 2 electrons there. Now, what we'll discover, and when we're talking about highest energy level, this is really in reference to valence electrons. And for us understanding bonding, valence electrons will be important in the representative elements, and we won't really think about them in terms of transition or intertransition elements. We can identify them, so I don't want to dismiss that. But in terms of bonding, we'll be doing bonding with representative elements. Those are the tall columns on the periodic table. So that's where our focus will be. So thinking about the highest energy level leads nicely into the definition of valence electrons. So valence electrons, by definition, are in the outermost energy level of the atom. So that's what valence electrons are. They are directly involved in bonding. So bonding is the result of chemical reactions. So the job of electrons is to get involved in these reactions. And it's not all electrons, it's these outermost electrons. Now, for the representative elements, the valence electrons can only come from S and P sublevels. So the maximum number would be 8. Okay, so that's a helpful thing to remember because it kind of can keep you on track. But valence electrons are always from the S and P. And if you recall how we get 8, the S sublevel only has 1 orbital, and so that can only hold 2 electrons. The P sublevel has 3 orbitals, so it can hold up to 6. So the maximum number of valence electrons is 8. Maximum number of electrons. And so I find these kind of things helpful to remember in test situations, in homework. Sometimes just knowing bits of information like this can help you catch mistakes. So if you ever find that you're writing down that something has more than 8 valence electrons, then take a second look because 8 is the maximum. Now, we were predicting valence electrons on the previous slide when we looked at the electron configuration, and we're finding the highest energy level and then counting how many electrons were represented. But if the question is simply how many valence electrons, we can rely on the periodic table. Now, this periodic table I have here is very small because the writing on the slide was covering most of the page and I didn't want to cover it. But I think you can get the idea, and if you have a periodic table that's next to you, you can look while I circle the numbers. So we're talking about here the representative elements. And the representative elements are these first two columns. It's all the tall ones, and then these last six. Okay, so we're talking about all of these here. And I don't want to write over the top of the groups because I want to look at those numbers. So these are our representative elements here. Now, how we can determine valence electrons quickly by using the periodic table is by looking at the group identification, the group numbers on the top of the column. So not all periodic tables will have both markers, but our periodic table has both the American Convention and the IUPAC designation. So in the American Convention, it's on our periodic table, it's the one that's closest to the table, and that's where you have a number and a letter. And the number in front of the letter, like if you look, I'm looking at this, oops, I keep hitting the wrong button, sorry. I'm looking at this convention, and so it's this number. So like the 1A has one valence electron. 5A has 5 valence electrons. If I went to the halogens here, 7A has 7 valence electrons. So it's very straightforward. You look at the group number, and whatever number is in front of the A is the number of valence electrons. Now, this is not true for these electrons here. Remember, this slide is referring to the representative elements, which is what we're going to be working with when we're thinking about valence electrons and bonding. Now, IUPAC, and I'll tell you what it stands for, but you don't have to memorize it, but it stands for, I think, the International Union of Pure, it's either Pure and Applied, I think it's Pure and Applied Chemistry. Pretty sure that's what it stands for. Okay, in fact, I paused the recording and double checked, and I was correct. I don't say it very often, so I was not sure of myself, but International Union of Pure and Applied Chemistry. And so it's one of the things, one of the groups that tries to organize, and so everybody's working on the same page. And so they use the numbers 1 through 18. Now, if you look at the numbers, that's fine for group 1 and group 2. So like group 2 would have just 2 valence electrons, so it's the same as the number. But if you go over onto the right side of the periodic table, it's like numbers 13, 14, 15. Well, we know you can't have more than 8. And what you do is you look at the second number. So like group 14 would have 4. If I went like the group that I did previously, 7A, it's group 17. And so it would be the second number. So this would have 7 valence electrons. So it doesn't change. We can't have more than 8. So that number is not the total number. But if you just take the second number, so you'll have a 1 and then another number. Just take whatever the second number is, and that will tell you your valence electrons. So it's pretty easy if the only thing you have to know is how many valence electrons, you just find that element and look at what group it's in. So we also can use, well, you know what? I want to go back. It just made me think, because if I was in class, I would give you an example. So let me give you, and it's hard to see here, but if you have a periodic table, go right here. Let's go to phosphorus. So how many valence electrons does phosphorus have? So maybe you got an idea. So I look up at phosphorus, and it is in, I'm just going to put it kind of here. It's in 15 or 5A. That's what group it's in. And so you could either look here or here, and it has 5 valence electrons. So that's all you would do. You wouldn't have to write it down, you would just look. Okay, now we'll keep going. So one way, and when we get into chapter 12, we'll be using this. Chapter 12 is, I go to chapter 12 after chapter 5. But our electron dot formulas, these are also known, and I probably call them this a lot, as Lewis dot structures. So these are the same thing, so don't get turned around by the language that's used. So electron dot structures, they take the symbol of the element, and then around it, using dots, they represent the valence electrons. So in this case, SY is just the meaning symbol, and they write up here core electrons. So what they're trying to tell you is that these type of structures are using dots for the valence electrons, and it's not like the rest of them have disappeared. They're kind of all just sitting in the symbol itself. So without any dots, you would think, oh, there's just the core or remaining electrons. Now, your book does have a specific way that it likes to write the dots. One thing I will mention is, like, if you think of the symbol, so I'll write P for phosphorus. I want to use a different color for what I'm going to do. Think of it as surrounded by a box, and you can have a maximum of 2 electrons on each side of the box. So they won't have all of the, like not all of them have all of them filled with dots. It depends on how many valence electrons. But the maximum you can have on any side is 2, and then that goes up to a maximum of 8. And we know that 8 is the maximum number of valence electrons. So if you follow this little illustration along right here, they're showing you how they're adding the dots around the symbol. So I will do it on the video as well. So if phosphorus was the center, so that would be the element symbol. Phosphorus is in group 5A. It has 5 valence electrons, so we would want to place 5 dots. Now, in your textbook, they start on the right side here, so 1. I'm sorry, let me make my dots a little bit smaller. Okay, that just looks like a giant dot. Okay, so 1, 2, 3, 4. So I go 1 on each side, and then I'm coming back around. So now I'm going to have one paired up. If I had, let's say I had fluorine, and fluorine is a halogen. It's in group 7A. So it has 7 valence electrons. If I'm following how your book does the electrons configurations, it would go 1, 2, 3, 4, 5, 6, 7. So 3 of the sides would have 2, and 1, and the top would just have 1. Now, as far as so that's how your book is doing it, and it's a good way. As far as I'm concerned, I'm not really worried about which side of the symbol you start on. But what I would be most concerned of is that you don't put more than 2 dots on each side, and you have the correct number of dots based on the valence electrons. Okay, so let me put this another way. Let's say you were trying to do phosphorus, and you put phosphorus, and then you thought, okay, phosphorus has 5 valence electrons, and you went like a smiley face, 1, 2, 3, and then 2 eyes, 4, 5. Like, this would not be a correct way to write our electron configurations. Oops, okay, that's okay. I can put I have to change my pen back and forth between how wide it is, and I don't like how wide that is. There we go. So that would not be correct, okay? So let's practice these two ideas of valence electrons and then Lewis dot structures for our atoms. So here are 4 different elements. I want you to identify how many valence electrons and then draw the Lewis dot structure. So go ahead and pause it now so you can do this on your own. Get some answers and then start the video again. And I encourage you to do this so you can, I know when you watch me, of course it makes sense, but you try to do it so you can see how far you can get with the idea. All right, so hopefully you did it. So what I would do, let's do sodium. So I would find sodium. I don't want to have red. Let me change to a different color. I would find sodium, and then I would look up here. So it has 1 valence electron. And I don't have a lot of room here. I'm just going to write 1 VE for 1 valence electron. My pen doesn't want to write the E. It wants to do something else. Okay, so 1 valence electron. So I would just say sodium with a dot. Okay. Aluminum right here. I look. It has 3 valence electrons. And so I would write the symbol aluminum. And according to your book, I'd go 1, 2, 3. Okay. Sulfur is right here. That's in 6A, so it has 6 valence electrons. So sulfur would be 1, 2, 3, 4, 5, 6. And then xenon is right here, which is a noble gas. It has 8 valence electrons. And so that would be Ze, 1, 2, 3, 4. All of them would be 7, 8. You'd have 2 on each side. Now that made me think of something that I don't think I've said, but if you look, helium, so all the noble gases have 8 except helium. It only has 2 valence electrons because since it's in the first energy level, all it has is a 1s sublevel. So, which is a 1s orbital, so it can't go up to 8. Helium does not have the p's available. So all of the noble gases except helium would have 8. Helium just can't fit it. It only has s. Okay, so that is about valence electrons and about drawing the Lewis dot structures. And we will be using both of this information in the future to help us understand bonding and how atoms get together. So, yeah, okay, good job.